Hello, and welcome back to AP Human Geography. Today I want to talk a little bit about why humans migrate. Lots of species migrate for all kinds of reasons, and actually, in many cases, the reason for humans to migrate is the same as any other species, and we'll talk about that in just a second. We are specifically focusing on human migration, and later on we'll actually talk about how we navigate, but we'll do that in a different unit. Okay, so here's your first mini quiz question. Although not everyone agrees on the dates, the current evidence strongly indicates that modern Homo sapiens, what? Did they evolve simultaneously, multi-regionally in Africa, Europe, and Asia? Are they direct descendants of Neanderthal? Did they evolve in Western Europe, or did they arise in Africa? Now, a lot of people actually want to say that we're direct descendants of Neanderthal, like the classic caveman, even though Neanderthal is not the caveman we are. And Neanderthals did evolve in Europe and the Middle East. We're not exactly sure where in there, but we really do think it's in Europe. And then they also wandered around, as did Homo erectus. So we're not the only human species to wander. We, like almost all of the other human species, arose in Africa. Our origins are in Africa. Our origins are actually in Ethiopia. And so when you mapped all of these fossil finds and you created this map, you can see that the heart of that was in Africa. So in a way, this was actually a review question. And then we spread out into Africa, and then we crossed somehow out of Africa. And then we moved into Europe, we traveled all along southern Asia, right? And eventually we make it all the way across the globe. We cross into North America. And how we get into the Americas is going to be the topic of its own class. But essentially we know that the Bering Strait, and you've probably learned this in another class, that at some point the Bering Strait was above water and created a land bridge. When was that? Well, for the last 110,000 years, there has been cycles of ice ages, right? And when the ice forms, lots of the geography changes, right? Because a lot of the oceans end up locked up in ice, or they end up locked up in ice. In some cases, the ice is so heavy that it pushes the continents down, and so you get seas, shallow seas, where there weren't any before. But as far as the Bering Strait goes, that happened in the last ice age of this cycle, and that was between 35,000 and 11,000 years ago. Okay, so now back to our original question. Why move, right? Ultimately, there are four big causes of migrations. Environmental changes, and that is something that we are going to be focusing on in early human migration, because environmental changes lead to what we call today economic pressures, right, for early man. So we see things like shift in climates, depletion of natural resources, hazardous events, right? Now, later on, we're going to talk about the global effects of migrations. We see some different effects of the earliest migrations, right? And we'll talk about what those are as this unit progresses. But essentially, our big stuff is going to be shifts in climates and natural hazards and loss of food sources, right? Now, those lead to famine, right? And the inability to sustain life. Now, in modern times, we can also throw in things like unemployment, overpopulation. We can throw in conflict. We can throw in forced migration. We can throw in better technologies in other places, or your technologies don't work. So those are all things that we'll talk about when we address modern migration. So we've actually divided migration into two events: the earliest human migration out of Africa, and then, all of the rest of it since the agricultural revolution, okay? Now, we can divide these factors into push and pull factors, and again, this is something that we are going to address a lot when we talk about modern migration. I've put this in here so you can see that ultimately, we're dealing with push factors. In in early migration, we're dealing with push factors, things that make you leave. In modern migration, we also have pull factors because we can know that there is some place, we are going to a place for a particular reason. It's pulling us there. If you're just leaving the area where you are, yes, you're going someplace new, but a lot of times you don't really know anything about it. I mean, when we left Africa, we didn't know anything about the rest of the world, which brings us to the other fundamental reason for early migration, and that's exploration. We are curious. We went because we could. It's the same reason we go to the bottom of the ocean and the same reason we go to space. We go because we're curious. We want to know what's there, and we can. And so that is, I think, equally a pressure for our moving around as these push factors. And I think I would consider that to be a pull factor, right? The appeal of the unknown, we can call it. All right, so how do we know that our migration paths look the way that we do? Well, you've already mapped fossil finds, right? And you found something that looks like this. And so what we know is that when we find human remains, we can date them, and that will tell us when those humans lived there. When we put all of the picture together, we get a great map like this. We start in Africa, we spread out through the Middle East, and then we take a hard left and go to Europe. We take a hard right and we go across Asia, and then eventually we end up in the Americas, and then after that we start populating the Pacific Islands. Now, an interesting thing about these fossils, and we're talking about the Americas, and again, this is going to be its own day, the skulls of the earliest migrants to the New World don't actually match those of modern Native Americans. So what does that tell us? That modern Native Americans are not descended from the early migrants. Skulls are an unreliable method of tracking populations because of human variation. Modern Native Americans have very different DNA than anyone else, and the skull haplogroup was not passed on. Well, all it says is that Native Americans probably did not descend from these early migrants that we have these ancient skeletons from, right? Skulls are actually a very reliable method for tracking populations, even with variation, because there are significant features that will be the same. And modern Native Americans don't have very different DNA from any other human, because no human has any different DNA. And then there's no skull haplogroup. That's not actually a thing. And remember, though, that haplogroups, and especially for those of you that took human evolution, haplogroups are those sort of genetic groupings that we use to kind of determine ancestry and stuff like that. Okay, and speaking of genetic evidence, the fossil evidence is really great, but we also have a genetic lineage that we can track, and most of that is done through mitochondrial DNA. Mitochondrial DNA, unlike nuclear DNA, is passed from one generation to the next completely faithfully, right? There's no recombination, there's no mixing, there's no half from one, half from the other, like you find in nuclear DNA, right? Nuclear DNA is genetic material from both parents, which is great because it tells you about both parents. But it's also jumbly, and recombination may have occurred, so it's not a faithful copy exactly. I mean, the sequences change because of crossing over and stuff like that. And this is mutations aside. So mitochondrial DNA, though, gives us a really good, solid, unrecombined track. Now, there's a problem with using mitochondrial DNA to track lineage. What is it? Is it that it degrades quickly? It's not accurate in predicting long time periods, it does not show the paternal lineage, or it's not passed on to male children? Well, I will tell you, it degrades as quickly as any other DNA, which depends on the conditions. It is accurate in predicting long times within a species, right? You're not going to do that for millions of years necessarily, but if you're looking at relatedness within a species, it works really well. It is passed on to male children because the mother provides the egg that makes the baby. And so it doesn't matter. You get your mitochondria from mom. It doesn't matter if you're a male or female offspring. It does not, however, show the paternal lineage because dad only contributes that other set of nuclear DNA, and he does not contribute anything else to the egg itself. I mean, he contributes in, that really important nuclear component, right? But as far as the egg itself, that's provided by mom. Okay, so what that means is that when you're looking at the inheritance pattern, anytime a woman has a son, right, that mitochondrial DNA lineage stops. Now, they will carry her mitochondrial DNA. So if you have their cells, then you can see what lineage they're in, but it's only mom's lineage. Dads are left out of this. And so in order to track males, we actually use Y chromosomal DNA. But the problem with Y chromosomal DNA is that it doesn't include females. And so you lose dad's mom, right? And her lineage. So there are big holes in these tracks because of the limitations of Y chromosomal DNA and mitochondrial DNA in the passing on of it, right? And so when you look at Y DNA, right, obviously it's going to be only males. So if dad only has daughters, that's the end of his line. If mom only has sons, that's the end of her line. All right, and when we put it all together, we get the same kind of map that you saw before, right? The fossils line up pretty well with the genetic DNA, although here is one small, and actually it turns out to be huge, difference that we've recently discovered. We can track mitochondrial DNA somewhere between 150 and 200,000 years. We can track Y chromosomal DNA about the same, and then we all end up with, one mitochondrial Eve and one chromosomal Adam. Now, these were not the only people alive. They're not the first of our species. They're just where that mitochondrial lineage and Y chromosomal lineage ends, right, as we go backwards. But it left out so many people. And it's not the beginning. We do now have fossil evidence of anatomically modern humans that dates back to 300 to 350,000 years. And so we're missing about 100,000 years of genetic information. And that's a very interesting thing. And it'll have very interesting changes on, one, how we think about ourselves in terms of how old we are, and two, it brings up a lot of questions about the genetics and how that works. And so it's really exciting discovery. All right, and then here, when we just put all of this together, you can see the human journey. And then, of course, I just love this picture because I love it that we walked here. Well, there were occasional boats, but for the most part, everywhere you see, we walked. We walked out of Africa across the globe, and that is amazing. And the question becomes, how did we do it, right? How did we actually do this? And that will be the subject of the classes, last class and this next class. All right, and that is it. If you have any questions, please let me know in class. Make sure you write them down. Thanks for listening, and I will see you next time.